Example 7. For each divisor R of M and S of N, the group Zm plus Zn has a subgroup isomorphic to Zr plus Zs. This is actually the group, this subgroup. M over R is an element of order R. It generates a subgroup of order R of Zm, and N over S generates a subgroup of order S of Zn, and this sum is isomorphic to Zr plus Zs. Theorem 8.2. Let G and H be finite cyclic groups, then G plus H is cyclic if and only if the order of G and the order of H are relatively prime. The proof follows immediately from theorem 8.1. If A is a generator of G and B is a generator of H, then the pair AB can be a generator only. Only this pair can generate the whole group. Of course, there may be other generators, but there must be a generator of this kind. And this will be a generator if its order is equal to the order of A times the order of B. But the order of the pair is the LCM of these two orders according to theorem 8.1. And the LCM of two numbers is the product divided by the GCD. So this, the order of the pair is equal to the product of A and B, if and only if the denominator is 1. And this is what the theorem states. Corollary 1. An external direct product of G1, G2, and so on, Gn, a finite number of finite cyclic groups, is cyclic if and only if G, the order of Gi, and the order of Gj are relatively prime when I is different from J. And the corollary 2 is similar, but the groups are replaced with the cyclic groups G and I. By using the result of corollary 2, we can express Z2 plus Z2 plus Z3 plus Z5 in different equivalent ways. Combine these two because 2 and 3 are relatively prime. Z2 plus Z3 is isomorphic to Z6, so replace it here, we get this. Then 6 and 5 are relatively prime, so Z6 plus Z5 is isomorphic to Z30, and we can replace this with Z30. Similarly, the same direct product is isomorphic to this, and then Z6 is isomorphic to Z3 plus Z2, and then combine these two, 2 and 3 are relatively prime, so Z2 plus Z3 is isomorphic to Z6. So the same group is isomorphic to Z2 plus Z30 and to Z6 plus Z10. So here prove that these two are isomorphic. But Z2 plus Z30 is not isomorphic to Z60 because 2 and 30 are not relatively prime. Group of units modulo n. Consider UK of n to be this set x in un such that x not k is equal to 1. For example, U7 of 105 is this: start with 1, add 7, add 7. If the result is relatively prime to 105, it stays. If not, you drop it. So you continue adding 7. 29 plus 7 is 36. 36 is divisible by 3, and 105 is divisible by 3, so 36 is dropped, it is not in the set. 36 plus 7, 43, relatively prime to 105, it stays. Plus 3, plus 7, 50. 50 is not relatively prime to 105, so it is dropped, and we continue like that. The result is a subgroup with 1, 2, 3, 4, 5, 6, 8 elements. So it is a subgroup of U 105, because any two numbers from here, if you multiply them, the product will be congruent to 1. Not 7. And they belong to UKN. Theorem 8.3. Suppose that S and T are relatively prime, then UST is isomorphic to the external direct product of US and UT. Moreover, US of ST is isomorphic to UT, and UT-ST is isomorphic to US. We are not proving this theorem, but we will use it. Corollary: let n be the probability of n1 and so on nk, where the GCD of ni and aj is 1 for I different from j. Then the group un is isomorphic to un1 plus un2 plus and so on plus unk. Since 105 is 3 times 5 times 7, and 3, 5, and 7 are numbers relatively prime in pairs, the corollary works. And we can write that U105 is U3 plus U5 plus U7. And there are other representations. We can write 105 as 7 times 15, and the corollary then implies this isomorphism. or we can write 105 as 21 times 5. 21 and 5 are relatively prime, so U105 is U21 plus U5. If we want to write UN as an external direct product of two groups, we can use the corollary. First, we factor n as a product of prime powers, and then we can use this fact. U2 is isomorphic to the trivial group generated by 0. U4 is isomorphic to Z2. U to the power 2n is isomorphic to Z2 to the power n minus 2 plus Z2 for n greater than or equal to 3. And if P is a not prime, UP to the n is isomorphic to Z P to the n minus P to the power n minus 1. So U105 is isomorphic to U3 plus U5 plus U7, and from what we know, U3 is isomorphic to Z2, U5 to Z4, and U7 to Z6. So U5 is written as an external direct product of Z groups. Similarly, U144 is U16 plus U9, because 16 times 9 is 144, and 16 and 9 are relatively prime. U16 from the previous is isomorphic to Z4 plus Z2, because 16 is 2 to the 4, and U16 will be 2 to the 4 minus 2, 2 to the power 2 is 4, plus Z2, and U9 is 9 is 3 squared, so we have Z 3 squared minus 3. 9 minus 3 is 6, so this is Z6. This way we can represent any U group as an external direct product of Z groups.